These are notes for Chapter 3, Exponential and Logarithmic Functions. We will be going through the notes packet at the first couple of pages. Okay, we will start. An exponential function is a function where the exponent is an x, it's a variable, and where the base, which is a, is greater than 0, can't be negative, and it can't equal to 1 either. It's all, and it can't be an imaginary number, it's going to only be a real number. We're going to review just for a minute exponent laws using S, T, A, and B. They're real numbers. A is greater than 0, not negative. It's not 0. And B is the same, not negative, nor is it 0. So the first one is where you're multiplying the bases that are same. You add the exponents. That's similar to x squared times x cubed, which we know to be x to the 5th. So you just add the exponents. The second rule that we use in the exponent when we're dealing with exponents, when we raise a power to a power, we multiply the exponents. A times a raised to the s times t power. Sometimes we have an exponent outside of parentheses, they're multiplied, the a and the b, so you can distribute exponents across multiplication. You cannot distribute exponents across addition or subtraction. 1 raised to any power is going to equal 1, including 0. Any base raised to a negative exponent will be 1 over that same base raised to the exponent. A to the 0 is 1 always. And why? Because when we have two bases that are the same, how do we get a to the 0? Where does it come from? It comes from when you have a fraction where the bases are the same, exponents are the same. When you cancel, is what you call it, a, you take the base and subtract the exponents, 1 minus 1, to get a to the 0, which is 1. We know that that's 1. We know that those two, if you cancel them, are 1. So that's where it comes from, a to the 0. By the way, 0 over 0, although it looks like it should be equal to 1, it's not. It's undefined. It's not equal to 1. Some facts about the graphs of exponential functions. That's where we're going next. Exponential functions are in the form y is equal to a raised to the x power. And they look like this. They have a domain of all real numbers. The range, they will have an asymptote at y equals 0, the horizontal asymptote. There is no x-intercept. If there's an asymptote at 0, y equals 0, there can be no x-intercept. In calculus, what this would be, if you have the function y is equal to a to the x, the limit, which is just the y value, the y limit of the function a to the x, when x gets bigger and bigger and bigger, or as x gets smaller and smaller and smaller, approaching negative infinity, will be 0, the y value. The function, this graph, when we graph it, we're going to use an example with base 2, y is equal to 2 to the x. So if x is 0, y would equal 2 to the 0, which is 1. If x is 1, y would equal 2 to the 1 power, which is 2. And if x is negative 1, y will equal 1/2. These are apparent x values that we're going to use to graph all of our graphs today. The parent for any of the exponentials, y equals a to the x, any base, is always going to be y equals 0. It approaches 0, as this limit tells us. This graph, when we graph these points, we get an increasing one-to-one function, which means that it's a function, and its inverse would be a function. That's called one-to-one. So the graph contains those points. These are just the coordinates of the points that we've got over here. And this graph is smooth and continuous. Note that it approaches infinity. As x approaches infinity, y is approaching infinity. As x approaches negative infinity, y is approaching 0. Another form, another parent that we're going to be used just for convenience It's the same kind of thing. Y is equal to a raised to the negative x. We'll say that that's the parent function. Really, it's the same as just 1 over a, 1 over the base, raised to the x. So in a sense, it's exactly the same as before. The domain is the same, all real numbers. The range is the same, from 0 to positive infinity. And again, there is no x-intercept. So for this graph, we will do the same exact kind of thing. Our parent, f of x, is equal to 1/2 to the x, which is a, 2 to the negative x. So it's the same thing. Y is equal to 1/2 to the x. We're going to graph that using our base x value, 0, 1, negative 1. When x is 0, y will be, if you look at y equals 1/2 to the x, y will equal 1. If x is 1, y is 1/2. If x is negative 1, y is 2. So we're going to graph those coordinates and the asymptote. And again, this is called exponential decay, by the way, because it's going down, but it's going to approach 0. And the one above it, number 3, is called exponential growth because it increases. So add that to your notes. Exponential growth as x moves from negative values to positive values increases, but as it for decay it decreases. Again, this graph is smooth and continuous. Going to page 2, we're going to introduce you to a constant that you met in Algebra 2. We've done this constant before. A constant is just a value that's used a lot, and this one is used a lot in all kinds of applications. It's called Euler's constant. It's also referred to as little e. It's pronounced Euler. Don't pronounce it Euler. That's not the correct way to pronounce his name, this guy. And in calculus, we can express this as in this, e is approximately the limit of this function as then it's getting bigger and bigger and bigger. It's approximately 2.7, etc. In class, I'll show you, we'll have a warm-up where you'll be able to understand exactly what this means. Right now, it doesn't mean a whole lot any more than if you just knew that pi was equal to 3.14, it wouldn't mean anything. But it is a relationship of some values that are very important. And so we'll talk about that when you get back to class. Okay, so graphing this is just another constant. Y is equal to e to the x. We graph it 0, 1, negative 1, our famous points, our parent points. And then if x is 0, then y is 1. Again, if x is 1, y is 2.7. And if x is negative 1, it's 1 over e, which is 0.37. And then we graph it. It looks similar to what we had before. The difference is it's a little flatter than the first one was, and in fact it's between, if you graphed them on a calculator, it would be actually between the graphs of y equals 2 to the x and y equals 3 to the x, which makes sense because it's 2.7, which is between 2 and 3. Okay, now we're going to graph a little more complicated problems using some transformations and similar to what we've done in the past. We've got a function, y is equal to negative 3 to the x over 2. And so the parent function we're going to find is y is equal to 3 to the x. We see a reflection over the x-axis. It's in front of the whole function. And we see a horizontal stretch. If you'll recall, the horizontal stretches are opposite to what it looks like it should be. You see x times 1/2. So it looks like the stretch would be 1/2, but actually when it's horizontal stretches, it's opposite. So it's actually going to be a horizontal stretch rather than a compression, and it's by 2. And then after you've done that, you're going to move the points up 1. So what we're going to do is we're going to graph the parent points. 0, 1, negative 1, 1, 3, 1/3. We just make a table just like that. Just those two columns, x and y. And then we know that there's a horizontal stretch, and we know that there's a reflection. We're going to let's go ahead and do the reflection first. And so that means that we will be taking each of the y values that we got from our parent function, and just multiplying by -1. So we take the y, -1. This is 3, so this will be -3. This is 1/3, so this will be -1/3. It's as simple as that. When you reflect over the x-axis, you're changing the value of the y. When you reflect over the y-axis, you change the value of the x. We have a horizontal stretch by 2, so we're going to take the x values, which are the horizontal components of the coordinates, and we're going to multiply each of the x values by 2. So 0 times 2, of course, is 0. 1, -1. Okay, so those are the points. The red ones are the ones we're going to actually graph. 0, -1, I've got them graphed right here. 2, -3, 2, -2, and -1/3. Now, with each one of those points, because we have a vertical shift up 1, we're going to look at each one of those points and move every point up 1. So we go here, we go up 1. From here, we go up 1. Here we go up 1. And then we actually graph. We know that the horizontal asymptote was 1, so now it's going to be was at 0, sorry. Now it's going to be at +1. And here's the graph. Okay? So it's as simple as that. You graph those transformed x and y coordinates and then do any vertical or horizontal shifts to each one of the points as you go. Now we can look at the graph and see that the domain's all real numbers again. The range, it goes from -∞, the lowest value, up to +1 because the asymptote moved up 1. Horizontal asymptote is at 1. Okay, let's look at the next one. Example B. And we see that we have y is equal to 3 to the -x plus 2. In order to do transformation approach, we need a coefficient of the x to be 1. And so we need to factor out that negative so that the coefficient of the transformed value is 1. So we'll factor out -1, and this, when we do that, the +2 becomes -2, as you can see. So you have 3, this is the same as 3 to the negative, parentheses, x minus 2, minus 4. Okay, so now we can look at it and see what the transformations are. We're going to reflect over the y-axis because now the negative is in front of the x value, the x variable, which means it's a reflection over y. That means when you reflect over y, the x values become negative. And so that's why it's negative of the x minus 2's. Okay, so you reflect over the x-axis, over the y-axis, then you shift to the right 2, and you're going to go down 4 each one of the points. So our parent function determined by this reflection is y is equal to 3 to the -x power, which is the same as y equals 1/3 x, 1/3 to the x power. So we're going to write out our parent coordinates, 0, 1, -1, and fill in what y will equal because it's 1/3 to the x. Okay, so x is 0, y is 1. If x is 1, y is 1/3. If x is -1, y is 3. So we're going to graph those points. There are no stretches or compressions. We've already taken care of the reflection by using this as our parent function, so you don't have to worry about that. So we're going to graph those points, 0, 1, 1, 1/3, -1, and 3. And then we're going to move each one of those points right 2 and down 4. So we're going to take this point and we're going to go right 2 and then down 4 points. This point we're going right 2 and then down 4. And we're going to we're going to go right 2 and then down 4. And those are the coordinates of the points of the new graph. And you can see the asymptote went down 4 units as well. So it's y is equal to -4 is the horizontal asymptote. The domain, you can see from this, is all real numbers. Range, -4 to infinity. Okay, we're going to go ahead and do C together so that you can get it into your notes correctly. And using this approach. The other videos showed a different approach. It's good. It's just a little different than what I like to do. I feel more comfortable with this one. I hope it makes sense to you. Okay, so here's our function. F of x is equal to 4 times 1/3 to the negative 2x. So our parent will be y is equal to 1/3 raised to the negative x. Sure, there's a transformation here, but we're just looking at the parent so that we'll know which points to start with. And this is the same, 1/3 and negative x is the same as y equals 3 to the x, so that makes this a lot simpler. So if that's the parent is 3 to the x, that's what we're going to be graphing. And we're also going to have a horizontal compression of 1/2. It looks like a stretch of 2, but remember that with the horizontals, it's always opposite. So it's a compression. It's not actually a stretch. So a horizontal compression of 1/2 and a vertical stretch of 4 because it's in front of the whole function. So it is a vertical stretch. The horizontals are always right in front of the parent, right in front of the x values. Okay, so here are our x coordinates and 0, 1, negative 1 again, as we've been doing. And when we fill that in, 3 to the x is the parent, 0, 1, 1, 3, those are our parent points. Now, we know that there's a vertical stretch of 4, so we're going to take each one of the y values, multiply by 4. And there's a horizontal compression of 1/2, so we're going to take each one of the x values and multiply by 1/2. That's where those points come from. These are the points that we're going to graph. There are no vertical or horizontal shifts, so we're ready to graph. The asymptote, horizontal asymptote, does not change. So we're going to graph these points, and there's the graph. And we can see that the domain stays the same, all real numbers. Range stayed the same as the parent from 0 to infinity, and the horizontal asymptote stayed the same. And now the last example, the graphing example, D, looks pretty complicated. 1 minus 3e to the x plus 2. So let's look at that and figure out what is the parent. When you look at this, it's just looks like e to the x is the parent. There's no transformation on the x at all. So, but we do see that there's a negative in front of the 3. We see a 3, the vertical stretch. So there's a reflection over the x-axis. There's a vertical stretch of 3. And it looks there's a horizontal shift where you go to the left 2. Remember, it's always opposite when it's horizontal. And a vertical shift up 1. Okay, so we'll start with our regular x, y values. And the x values 0, 1, negative 1, and put them in order this time, negative 1, 0, 1. And so when x is negative 1, y is 1 over e, which is 0.37. When x is 0, y is going to be e to the 0, which is 1. And when x is 1, y is 2.7. Now, to take care of the reflection over the x-axis and the vertical stretch, those are changes to the y value. So we're just going to do both of those at once. And just look at each one of the y values, multiply by negative 3 to get those points. So now we're going to graph those points, those 3 points. Negative 1, 1.1, 0, negative 3, and then 1, negative 8.1. And then each one of those points, we're going to move to the left 2, up 1. So left 2, up 1. Left 2, up 1. And then this one's going to the left 2 and then up 1 as well. And then we see that since it's going up 1, the asymptote's going to go up 1 also. And here's a graph of the function. All done. And we can see that the domain is all real numbers. And the range. The lowest value is negative infinity, the highest value is positive 1, and the horizontal asymptote is y equals 1. Okay, that's it. You have what you need now to do your homework for the graphing. Watch the next video to do exponential equations.